Imagine driving across town. You take the direct street, only to end up dead in your tracks behind a massive wall of red brake lights. Meanwhile, just a mile over, cars are cruising along a much longer, winding highway without a single delay. It's a frustrating lesson of the road. The shortest physical distance to your destination does not guarantee you'll get there first. The global internet deals with this exact same geographic headache every millisecond. Billions of data packets constantly need to find the most efficient route across sprawling physical networks. If you know how to pull out your phone and use a GPS app to route around a traffic jam, you already have an intuitive grasp on how the smartest routers on the internet operate. Early networks didn't have that kind of awareness. Legacy routing protocols, like RIP, operated on a rigid, simplistic metric called the hop count. Looking at a network map like this, a hop count system measures distance blindly. It only counts the individual routers sitting between point A and point B. The route on the left takes 2 stops, while the route on the right takes 5. The system automatically defaults to the 2 stops. It completely ignores the actual bandwidth, the raw speed, of the cables connecting those devices. This creates massive bottlenecks. Data gets crammed onto ancient, agonizingly slow copper wires simply because the math says it requires fewer physical steps. As network demand scaled up, the infrastructure required a completely different approach. We needed a protocol prioritizing the speed of the road over the number of intersections. That brings us to OSPF. Open Shortest Path First, or OSPF, solves the traffic problem by operating with total situational awareness. It refuses to make a single routing decision without seeing the entire board. To get that view, an OSPF router boots up and immediately shoots out communication pulses to its neighbors. These pulses are called link state advertisements, and they trigger a chain reaction of responses across the topology. The router compiles all these incoming responses into a master ledger known as the link state database. Older protocols only asked their immediate neighbors for blind directions. An OSPF router holds a comprehensive 3-dimensional map of the entire network architecture before moving a single byte of data. With the map built, OSPF needs a way to evaluate the quality of those connections. It does this using a metric simply called cost. Looking closely at these connections, OSPF calculates cost based on a strict inverse relationship with a cable's raw bandwidth. The faster the link, the lower the mathematical penalty. A blazing fast fiber optic line can move massive amounts of traffic instantly. Because it is highly desirable, OSPF assigns us the tiny cost value, in this case, just 5. Conversely, an outdated low-bandwidth connection is a major liability. The protocol stamps it with a massive cost penalty of 50. By translating bandwidth into these numbers, OSPF strips away the physical hardware entirely. Instead, it turns the network into a pure mathematical landscape, where poor speed is simply quantified as high resistance. Now the router needs an engine to process all that cost data. It runs a calculation called Dijkstra's algorithm. Let's test this engine by plotting a course. Starting here at router A, we want to reach the target on the far right. The algorithm first looks at the most direct physical line, going straight through the middle. It calculates the values in real time. The first cable hits us with a penalty of 50, plus 10 for the second leg, resulting in a total route score of 60. That direct line requires the fewest jumps, but the final score is terrible. The algorithm clearly identifies the sluggish bottleneck hiding right in the middle of the path. So the algorithm tests an alternative. It maps out a route that weaves up, across, and back down, passing through several extra routers along the perimeter. A legacy hop count system would immediately discard this option. 4 jumps instead of 2 looks inefficient. But Dijkstra's algorithm tallies up the actual connection speeds. 10 plus 5 for the fiber link plus another 10 equals a total route cost of exactly 25. 60 versus 25. The route with the longer physical distance has less than half the mathematical resistance. The protocol actively chooses to send the data the long way around. By taking more physical jumps, it leverages those low-cost fiber connections for significantly faster delivery. Zooming out, you see a holistic network moving massive data flawlessly. Packets constantly reroute around slow cables, taking counterintuitive paths to maintain peak speed. For anyone studying networking, this redefines the name Open Shortest Path First. In the world of modern routing, the shortest path never means taking the fewest physical steps. It means calculating the path of least mathematical resistance.